Alright, so the next topic in the alternating series test is the alternating series remainder estimation theorem, commonly known as ASRET for short. Alright, and well, here this estimation theorem tells us that if an alternating series converges and the first n terms are used to approximate the infinite sum, then the value of the remainder or the error term is less than or equal to the first neglected term. And well, in other words, here is a formula which is very simple, you know, so in the sense that the number of terms and all that, but you'll see how it works. So this Sn, or rather the S, so the sum, the actual sum will be, for instance, if we use the sum of the first 55 terms, then well, there is a remainder of using the first 55 terms, you know. So of course the sum, the infinite sum, won't be accurate, won't be the actual value. It will be off by this remainder, and this remainder R7 is less than or equal the first neglected term. For example, if we use the first, for example, the first 4 terms, so the absolute value of the remainder of using the first 4 terms will be less than or equal the next neglected term. So if we're using 4 terms, then it would be less than the 5th term. If we use the first 173 terms, well, the error will be less than or equal the next neglected term, which is a sub 174, and so on, right? So that's the idea. Now, what's the picture anyway? So, well, so this is the picture of how an alternating series behaves ultimately, you know. So, for example, so if we look at this series right here, well, so notice this series will converge to this value right here. Eventually, the sum will be around this value, right? And the thing here is, well, what happens if I'm only at the first term, which is the sum, which I estimate the sum using the first term? Well, so notice that in this case, I will be off from the actual sum S by what I would like to call R1. And this R1 will be less than or equal to the next neglected term, in this case the second term. And in fact you could for example compare this R sub 1 with this second term. Isn't it true that this remainder is less than the second term? The remainder of the first term is less than the second term. See, this bar is smaller than that longer bar. All right. Let me show you another example. Now, what if instead I use the second one, so the sum from the second? Well, if I do that, well, I'm gonna be off from the actual sum by what I would like to call R2, the remainder 2. And this value is indeed smaller than the value of the next term. You see how that's smaller than that? And same, let me just do one more. If I use the third estimate, and the third term to estimate, in this case, well, I will be off by R3, and this R3 is of course smaller than a sub 4. All right, so that's the picture of what this alternating series remainder estimation theorem is. Okay, so let's look at a couple of examples to see what this is about. Well, so let's consider the series sigma n equals 1 to infinity of -1 to the n plus 1 and 1 over n squared. Okay, so number one, I'm going to expand a few terms, I guess more than just a few terms, because I'm going to need a few. I'm going to need quite a few. 1 minus 1 fourth plus 1 over 9 minus 1 over 16 minus 1 plus 1 over 25 minus 1 over 36 plus 1 over 49 minus 1 over 64 plus 1 over 81 minus 1 over 100, and of course this series goes on forever, but I don't need that many, just a few. Okay, the thing here is, if we use the first 5 terms, all right, if the first five terms are added, well, then this will approximate the sum with an error of no more than the next neglected term. And then, well, when we consider 1, 2, 3, 4, 5, the first 5 terms, well, the next term, that's the first neglected term in this case, it's 1 over 36. I know it's a negative, but I mean, of course, keep in mind that this error inequality right here, it has an absolute value, and it could be plus or minus that value. All right, so coming back to this, well, if instead 8 terms are added, right, so I'm going to add the first 8 terms instead, what happens on that case? So that's a 5, 6, 7, 8. So 8 terms. First 8 terms, well, the next one, the first next neglected term will be 1 over 81. All right, so that's the maximum value of the error in this case. Now, in some cases, we may need to know how many terms are needed in order to an error to be no more than certain order of magnitude. In particular, for this exercise, we want to know how many terms do we need in order to the error will be no more than 0.05. That is, in more understandable terms, I guess, that the error is no more than 0.1%, which is a decent amount of error. It's not that bad of an error, right? Well, in order to find out, let's use that inequality, that remainder theorem, which in this case is, well, it's r sub n, or the absolute value of r sub n is less than or equal to a sub n plus 1, which is, in this case, we want to make this less than 0.001. All right, so what we're going to do, the a sub n plus 1, we're going to replace n with n plus 1 in our original series, but recall that the a sub n, it's only this quantity right here, all right, without the alternating factor. That is, I'm going to replace 1 over n plus 1, but in this case it's squared, less than or equal 0.001. But to handle this inequality in a lot more easier way, I'm going to rewrite this 0.001 as 1 over 1000. All right, and then, well, to keep working with this inequality, let's solve the inequality for n. Well, notice, by properties of inequalities, we can flip the inequality, n plus 1 squared greater than or equal 1000. That's one of the properties of inequality. Just flip the inequality and reverse the direction of the inequality sign. It's just like when you have 1/2, which is greater than 1/3. All right, if you reverse the inequality or you flip the inequality, this is 3 and 2, but in order to keep the logical sentence, well, 3 is greater than 2. All right, well, let's see, what about it? So the square root of 1000, well, so I know you might be thinking, well, this should be plus or minus. using the square root property, but in this case, since we're dealing only with positive values of n, so n plus 1, and n is greater than or equal the square root of 1,000 minus 1, and n is greater than or equal approximately, oh actually this is, let me write it this way, approximately 30.6. But of course, remember, let's recall that we don't have like the 1.5th term of a sequence, or you don't win in a competition, you don't win the second and a half a place, no? So it has to be integers only. So in this case, n has to be greater than 31. All right. So this means that in order to estimate the infinite sum, or to estimate the actual sum right here, and ensure that the error is no more than 0.1% or 0.001, then you will have to at least use 31 terms or more in the sum. All right, let's look at another example, and we have let's consider the series sigma n equals 1 to infinity, negative 1 to the n plus 1 of 1 over n factorial. All right, so in this case, again, let me expand a few of the terms. So that's equals to 1 minus 1 over 2 factorial, which is 2, plus 1 over 3 factorial, which is 6, minus 1 over 4 factorial, which is 24, plus 1 over 5 factorial, which is 120, minus 1 over 1, 2, 3, 4, 5, 6 factorial, which is 720. And let me make this 0 look like an actual 0. Yes, all right. So in this case, let's use the first 4 terms to estimate the sum. All right, just the same way we did it before. So 4 terms. So use the first 4 terms to estimate the sum. What is the maximum amount of error in this estimation? And then the question is the actual sum greater than or less than the estimation? Well, number 1, let's figure out the maximum error. Well, for using 4 terms, we will use the first neglected term in this case, which is 120, 1 over 120. Now the question is the actual sum greater than or less than this estimation? Well, so this is going to take us to the original picture of how the alternating series test looks like. Well, so depending on what was the last operation that we did over here, so we may be underestimating the sum, that is getting a value less than the actual sum, or we may be overestimating the value of the sum, that is we're getting a number above the actual sum. And this depends this depends on what was the last operation that we did. In this case, we are adding, then we are subtracting. All right, so, and then we're adding again, subtracting, adding, subtracting, etc. So notice that when we subtract, if our last operation was to add, well, then we end up at a value above the actual sum. But otherwise, if our last operation that we do is below the actual sum, then we will be underestimating the value. So in this case, well, so in this case, because we're using 4 terms, and the last term that we consider in this case, it's a minus, well, then we are ending up below. All right, so less. And that's below the sum. And well, same idea, how many terms are needed in a way that the error will be no more than 0.01, which again is 0.1% off, as much as 0.1% off. Okay, so let's set up the inequality. So Rn, absolute value of R sub n, less than or equal a sub n plus 1. less than or equal 0.001. Alright, so that's a 1 over n plus 1 factorial. Is that less than or equal 0.001? Well, so let's rearrange to make it easier to work with. N plus 1 factorial less than or equal 1 over 1000. And let's fix the inequality. N plus 1 factorial greater than or equal 1000. And well, here is the thing. I don't think in your previous intermediate algebra classes you have solved inequalities involving factorials. In fact, we hadn't. So in this case, what we're going to do is guess by computing some of the factorials of numbers and then compare whether each factorial is greater than 1000. For example, 5 factorial. Well, 5 factorial is 120, but 120 is not greater than or equal 1000. So no. Okay, 6 factorial. That's 720. No, that's not bigger than 1000. Well, 7 factorial. That's 7 factorial. That's 5040, I believe. I forget what this number is. 5040. 5040-ish. And well, this number is clearly greater than or equal to 1000. That means in this case that 7 factorial is okay. Yeah, I already said that thing. That's greater than 1000, which means, be careful here, it means that n plus 1 has to be equal to 7. N plus 1 equals to 7, n equals to 6, which means that we need 6 terms. Alright? And the very last topic for alternating series is rearrangement of series. Well, so what happened? Well, what about this one? Well, so when a finite sum, with a finite sum, we can arrange the terms without changing the value of a sum. For example, let me give you a 5 plus 4. Now let me make it easier. So 1 plus 2 plus 3 plus 4. So that's equals to 10. But also 3 plus 4 plus 2 plus 1 is also equal to 10, right? If you rearrange these numbers, you should get the same value. All right, but the thing here, and well, it all stems from the fact that these numbers follow the commutative and associative properties of addition. But in this case, however, this is not necessarily true for an infinite series. It is still true for a series that converges absolutely, right? If you have one of those series that converge absolutely from the previous pages for this handout, for this section, well, you should have no problem with this idea right here. All right. However, when a series converges conditionally, unfortunately, rearranging the terms would give a different sum. And let me give you an example on how that happens. Okay. So let's see. Let's consider the series sigma n equals 1 to infinity when negative 1 to the n plus 1 times 1 over n. So let's find the sum without grouping the terms. So okay, so let me call this S. This is 1 minus 1 half plus 1 third minus 1 fourth plus 1 fifth minus 1 sixth plus 1 seventh minus 1 eighth plus 1 ninth. I'm gonna need a few actually. Minus 1 over 10 plus 1 over 11 minus ... Goes on forever, all right? Okay, so let's find the sum regrouping this. Okay, so how am I going to regroup this? So this is what I'm going to do. I'm going to regroup these values right here. This, well, s equals to, so this is what I'm going to do. I'm going to put together the negative 1/2 with the negative 1/4 right here, and then I'm going to put together the 1/3 with a negative 1/6, and then I'm going to leave the 1/8, and then the 1/5 I'm going to put it together with a negative 1/10. So you'll see what's going to happen here. So let's see, so let me write it down. That's 1 minus 1/2 minus 1/4 plus 1/3 minus 1/6 minus 1/8 plus 1/5 minus 1/10. And even though you're not seeing the next number, I didn't write the negative, the plus, the minus 1/10, 1/12 rather. Well, it's there, and then finally that 1/7 is gonna show up here, and I'm gonna put it together with a negative 1/14, which you don't see either. All right, I'm just gonna put plus dot dot dot. All right. So what we're gonna do here is the following. So I'm going to simplify these two. 1 minus 1/2, 3 1/3 minus 1/6, 1/5 minus 1/10, 1/7 minus 14. The remaining terms I'm just going to leave them alone, and you'll see what's gonna happen. So s equals 1/2. So these two are gonna be the 1/2. And then I'm gonna put this together. I'm gonna add these two. 1/3 minus 1/6, and well, let me write this down. Minus 1/4 plus 1/3 minus 1/6. That should be 1/6. All right, and minus 1/8. 1/5 minus 1/10. That's 1/10. And should use different color to highlight this one. And then minus 1/12 plus 1/7 minus 1/14. Well, let's use a different color to highlight this one. So yeah, that's gonna be 1/14 plus dot 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 that goes on forever, or rather minus, right, if you prefer. Okay, so observe this series right here. So that's 1/2, 1/4, 1/6, 1/8. Notice all these numbers have a 1 factor of 1/2. So, and that's when I do this, well, I'm going to obtain the following. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7, etc. But what's this? Hey, isn't this actually also s, which means s equals 1/2 the sum? All right, this is so weird. How is something actually half of itself, huh? This is weird, which leads to 1 equals 1/2. All right. So, well, so for this last example, well, I just want to mention that you don't have to worry about this for anything on the exam or even in the homework. This is only one of those mathematical curiosities of something about how numbers behave, in particular how the rearranging of an infinite series, an alternating series that converges conditionally. In this case, its value gets affected when we rearrange the sum of its terms. This doesn't happen with finite sums as we did before, with sums of a finite number of elements, or with infinite series that converge absolutely as opposed to conditionally. And this is a good place to quit the video. This is the end of this section.